Alrighty, so um, let's have a look at the multiple roots of a polynomial. So we've learnt before that if we consider multiple roots of a polynomial, we know that there's certain properties of multiple roots. So we know that, for example, if you have an even power, we call that a double root, and if you have an odd power, we call that a triple root. Now, we've learned in the past before that a double root reflects upon the x-axis, and so it bounces off, and a triple root, or a root of an odd power, will inflect through the x-axis. It kind of is like a little curve. So question number 2 says, find the roots of x cubed minus 9x squared plus 14x and state if they're multiple roots. So I'm going to factorize this. That's going to be x squared minus 9x plus 14. And if we factorize that again, it's going to be x minus 7, x minus 2. If we make that equal to 0, our zeros are going to be 0, 7, and 2. So, therefore, no multiple roots. So a multiple root would occur if we had more than this. If we had the same number occur more than once. So if we had 0, 7, 7, 2, then 7 would be a double root, so we would have multiple roots. Okay, question 3 says a polynomial of degree 3 has a triple root at 1. Part A, write an expression. Is this unique? Well, if we've got a polynomial, it's going to be y equals, a root of 1 would have to have x minus 1 somewhere, and it's a triple root. Now, is this unique? No, it's not unique. For example, y is equal to 2 x minus 1 cubed. That still has a triple root at 1, but it's not the same as the other one. So y is equal to 3x minus 1 cubed, and 4 and 5 and minus 1 would all be valid solutions. So no, it's not unique. Part B says, if p of 2 equals 5, write the expression for the polynomial. Well, if we know that any number can exist outside of here, well then we've got y is equal to a x minus 1 cubed would be a generic form of my polynomial. The question says 5 is equal to a times by x, which is 2 minus 1 cubed. 5 is equal to a times by 2 minus 1 cubed, which is 1. So a is 5. So our polynomial is 5x minus 1 cubed. Okay, so we can use this information to graph polynomials. So question 1a says, examine the behavior of the polynomial x plus 2 squared brackets x minus 1 close to its multiple roots, and describe how this graph affects the roots. We do that by constructing a table of values. So we're going to put our x values here and our y values here. And we're going to do that first of all for the first root of minus 2, which is this one here. We're going to plot minus 2 in the middle and consider points all the way around it, minus 3 and minus 1. If you substitute in minus 3, you get a negative number. If you substitute in minus 2, you get 0. And if you substitute in minus 1, you get a negative number. So something like this has occurred. We get a negative number, and then a 0, and then it becomes negative again. So that has occurred. Now that's what we expected because it's a double root, so it has to reflect, or it has to bounce off the x-axis. If we can now consider the second root of 1, we draw a nice table of values. This is x, this is y. We put 1 here, I might put 0 here and 2 here. If you substitute in 0, you get a negative number. If you substitute in 1, you get 0. And if you substitute in 2, you get a nice positive number. So that's exactly what we expected. We expected a negative number, and then 0, and then it to become positive. So if this second value here was negative, that's not what we are expected, because x minus 1 is a singular root, so it has to reflect through the x-axis. Inflect, sorry. So it's a bit squiggly. Describe the limiting behavior of the polynomial. Limiting behavior means what happens at plus and minus infinity. We do that by substituting in p of 1,000. So all of this stuff we've talked about before, but I haven't formally shown you. So if we substitute in p of 1,000, it's going to be 1,000 plus 2 squared times by 1,000 minus 1. That's going to be a very large positive number. So the limiting behavior at positive infinity is a large positive number. We consider in the limiting behavior at negative infinity, we substitute in a very small negative number like minus 1,000. So minus 1,000 plus 2 squared minus 1,000 minus 1. And if you do that, you get a negative number. So as x is negative, or x goes towards negative infinity, we get a very, very small negative number. Or it's a large negative number, but technically that means it's small. Okay, so sketch the polynomial. We're going to graph our roots of 2 and 1. Now we know that it has to start up here because the limiting behavior of the polynomial is as x goes towards infinity, as x gets larger, your y is a positive value, and it has to end down here. So your graph has to start up here, it has to go through 1, and it has to do that little squiggly line. Now let's look at our y-intercept. Our y-intercept is going to be 2 times by 2, 4 times by minus 1, which is minus 4. So we plot minus 4, we're going down to minus 4, and then it has to turn up to get to this root, and then it has to turn around there. So it needs to turn up to get up to minus 2, but minus 2 is a double root, so it has to flip and go back down. Okay, draw examples of a polynomial with a double root at 1 and a leading term of x minus x cubed. This tells me it's a negative cubic function. Now what we know about negative cubic functions is that they must start up here and end down here. So all we have to do is have a double root at minus 1. So it has to start up here, so it has to come down, then it has to come up, but it has to end down there, so it has to turn around. So that's our function there. It has to start, because it's a negative cubic, it must start in the second quadrant and then end in the fourth quadrant. And it has to have a double root at minus 1, so it has to turn around. Number 3, a polynomial has a double root at 2 and a double root at minus 3. Its leading term is 2x to the power of 5. Now remember, anything that is an odd power looks like a cubic. And this is a positive cubic, or a positive function that looks like a cubic. Now we know that positive cubic looking functions have to start up here and end down here. Now we also know that there's a double root at minus 3 and 2. So it must start down here, then it's a double root here, so it must turn around, but then it has to go up, back up, so it can get to 2, but 2 is a double root, so it needs to turn around. But we know that it must end up here, so it has to turn around again to go back up there. Now the question says, by sketching the graph, show that the polynomial has another root in the domain x is greater than 2. So we'll say another root must exist. So a root x is greater than 2 must exist as our function must end in first quadrant. And a bit more formally, you might say, as x goes towards infinity, your y must also go to infinity. That's telling me as x gets larger, our y must get larger, not smaller and not down here. Okay. Question number 4. A polynomial has a double root at 2 and a double root at minus 3. Its leading term is 2x to the power of 5. So this is telling me it's a positive function and it's cubic looking. So we know that it has a double root at 2 and a double root at minus 3. So we're going to draw this. Oh, this is the same as before. Sorry, this is the same question. A double root at 2 and 1 at -3, so we know it has to go like this, and then like this, and then like this, and like this, but then it has to go up like that. That's just the same as before. Number 5. Now, number 5, I think there's a mistake. This has to be odd. Okay, so draw a nice graph. Sketch a polynomial whose only roots are a double root at 3 and a triple root at -1. How do you know that this graph has an odd degree? Okay, yeah, so that's definitely, it has to be odd. Now, there's a few reasons that we know it's odd. Well, you've got 2 roots here and 3 roots here, which means you've got a total of 5 roots. So it has to be odd because you've only got a total of 5 roots because it says there's only that many roots. But graphically, we're going to plot a root at 3 and also 1 at -1. And there's 2 possibilities. Our first possibility is that it comes down here and then it turns around because it's a double root at 3, and then there's a triple root at -1, so it has to look like that at -1. Our other possibility is that it comes here from downwards, turns around, and then goes up and goes in like that. So it's just the same in reverse. But it has to have an odd degree as for it to be even. Now remember, if your polynomial has an even degree, it has to start and end in the same direction. So it must start in the first quadrant and end in the second quadrant. So it must start up here and end up there. Or it must start down here and end down there. So for it to be even, there must exist either roots x is less than -1 or x is greater than 3. However, there are no more roots. Therefore, it is of odd degree. So, in a nutshell, I've got my function and it comes down here and it goes up and then it turns around and goes through here. For it to be even, it would have to turn around and then go back up there. But that would mean there would have to be a root here. There is no root here. So it can't be even. If you were going the other way, it would have to come up here and then go down here and then go down here and go down here. But it would have to turn around and go up here. And there would have to be some sort of root here, but there is no root here. Because we're told in the question, it only has those roots. So it must be odd because there are no extra roots. Okay, hope that makes sense.